Welcome students to a continuation of our lesson on implicit differentiation. Last time that we met, we were just working on a brief introduction to what is implicit differentiation. Today we're going to take it one step further, and we're actually going to find a second derivative implicitly. So just a quick recall, that would be when we have a function that is not solved explicitly for one variable, and we're going to take the derivative of both sides. We will do a quick review as we go through this process because we will have to do the first derivative before we do the second derivative. The process that we're using is the same that we've used for functions that were explicitly defined, but this time we're going to do it with implicit differentiation. So feel free at any point to pause the video, try it on your own, or if I am going too fast, of course, pause it, replay so that you can follow what I'm doing. So first thing we're going to do is we are going to take the first derivative. So if I take the derivative, we can write it. Eventually we'll probably stop writing this. If I take the derivative of the left side, I'm going to get 2y, and recall that I need to follow that by dy dx because I just took the derivative with respect to y, and I need the derivative with respect to x. Equal to derivative on the right side, derivative of x is just 1. And of course I want to solve for dy dx, so I'm going to keep that on the left side, and to solve for it I'm going to divide by 2y, and I'm going to get a lovely dy dx is equal to 1 over 2y. I am going to kind of box this, mark this, because there's a chance I'm going to need this later on in the problem. And now I'm going to continue on, and I am going to take the second derivative. So let's switch colors here so you can follow that I am now doing the second derivative, which is going to be, recall our notation for writing the second derivative. Of course, this is just one of them. Second derivative is going to require either a quotient rule when I'm looking at the right side, or I can actually rewrite that. And you can do whatever you want. I'm going to go ahead and rewrite that as 1/2 times y to the negative first, because then I can just use my power rule and not have to use my quotient rule. So if I'm using my power rule, then I'm going to have 1/2 times a negative 1 y to the negative second. Be careful. We do need to multiply that times dy dx because we just took the derivative with respect to y. We need the derivative with respect to x. If we tidy up what we have for our second derivative, let's see, we've got negative 1/2, I suppose, and then we have y to the negative second. So I'm going to go ahead and throw that in the denominator. 2 to the, that is not what I meant to put. 2y to the second power, positive second power. And then I've got this times dy dx over here. Is that in the numerator or the denominator? Hopefully you just answered that that's in the numerator. So I'm going to put that in the numerator. And I'm essentially done as far as tidying it up, but I want my second derivative to be with respect to x and y, and therefore I should not have a dy dx in it. So I'm going to take my dy dx and I'm going to replace it with, remember when I marked this off before, with what dy dx is equal to. And dy dx is equal to, if you go right up here, 1 over 2y. So I'm going to give myself a little more room here. And I'm going to rewrite that as negative 1 over 2y. That's my dy dx part, over 2y squared. And of course that just looks a little messy because now I have a complex fraction. So I'm going to go ahead and simplify my complex fraction, a little bit of algebra, times 1 over 2y squared in the numerator and the denominator. Allows my denominator to cancel out. And come on, get over there. If I tidy that up, let's see, in the numerator I've got negative 1 in the numerator, 2y times 2y squared, giving me altogether 4y cubed in my denominator. And that's your final answer. We should note that that's our second derivative that we just found, negative 1 over 4y. That's a 3 in the denominator. So just a little recap of what we did before you go on and try the next problem. I wish it would let me move all this at once. Apparently it's not going to. We did the first derivative, and then once we did the first derivative, we took the derivative again, but we did need to make a substitution. That's going to be a theme that you're going to see here, that when we have our first derivative, when we take the second derivative, you are going to end up with a dy dx. You're going to have to substitute what it's equal to, and then you might have to do a little bit of algebra gymnastics to simplify things up a little bit. Okay, let's try another one.